wings that sweep back and forth, turn over at every reversal, and continue supporting the body in both directions. To understand why that is so unusual, it helps to begin with a more ordinary bird. For most birds flying slowly, the downstroke does most of the useful work. During the upstroke, the joints flex, and the wing presents less area to the air. That makes an efficient recovery stroke, but gives little weight support. A hummingbird cannot rely on that pattern while hovering. With no forward speed to carry it between strokes, the average upward force from its wings must equal its weight, while the average horizontal force must be almost zero. It has to manufacture its own airflow, then use both halves of the wingbeat. The transformation begins in an unusually specialized shoulder. Instead of producing the stroke mainly by raising and lowering the upper arm, a hummingbird rotates the humerus, the upper wing bone, strongly around its long axis. Its relatively stiff hand wing remains extended through most of the cycle, sweeping through a broad, nearly horizontal arc. Near each reversal, the shoulder apparatus rapidly pitches the wing, changing which edge meets the air and reversing its angle of attack, the angle at which the wing cuts into the flow. The return stroke is not an unloaded recovery. The working surface has been turned over so that it can push air down while traveling the other way. This three-dimensional motion often gives the wingtip a shallow figure-8 path when viewed from the side. That description is useful, but it is not the explanation for hovering. The loop varies with viewpoint and flight condition, and in faster flight, the familiar shape can largely disappear. What matters is the combination beneath it. Back and forth sweep, smaller vertical movement, and precisely timed wing rotation. The result is useful weight support on both halves of the cycle, but not equal support. Early wake measurements on hovering rufous hummingbirds attributed roughly 3/4 of weight support to the downstroke and 1/4 to the upstroke. Later, direct force measurements on Anna's hummingbirds put the upstroke contribution at about 28%. The exact balance varies with species, kinematics, and method, but the robust finding is asymmetry. The upstroke matters greatly, while the downstroke remains stronger. A bird wing is cambered and structurally asymmetric, and the outer wing inverts more completely than the region near the body, so reversing the stroke does not create a perfect mirror image. The wing also experiences profoundly unsteady airflow as it accelerates, slows, and rotates. At the high angles used in hovering, air rolling around the sharp leading edge can form a vortex. By helping maintain low pressure over the wing, it can augment force beyond a steady flow prediction. Measurements and simulations show this vortex is important, especially during the downstroke, but its strength and contribution vary. It is one contributor, not a permanent suction tube carrying the bird. Wing rotation and acceleration around reversal also affect the force, and the wing may meet air disturbed by its previous motion. Their combined result is clearest in the wake. Experiments reveal organized vortex loops and fast downward flow beneath the bird. The details differ among conditions, but the meaning is simple. The wings give downward momentum to air, and the reaction on the bird is upward. Once the bird can create that force, maneuvering becomes a problem of aiming it. In a steady hover, the horizontal components nearly cancel, leaving an average force directed upward. To accelerate forwards, the bird changes its body angle, stroke plane, and wing pitch, so the combined force tilts forwards as well as upwards. To retreat, it pushes air partly forwards and receives a backward reaction. Measurements show that backward flight uses a more upright body and altered stroke plane geometry. It is not simply forward flight in reverse. The same force vectoring principle works sideways without requiring the bird to turn first. The two wings do not have to perform identical strokes. A hummingbird can change their amplitudes, stroke planes and rotations independently, creating unequal forces that roll, pitch, or yaw the body. Its low rotational inertia helps it turn quickly, but also makes it vulnerable to gusts. In turbulent wind experiments, hummingbirds varied stroke amplitude from beat to beat and used greater left-right asymmetry. In roll perturbation experiments, they adjusted muscle recruitment and wing rotation between the two sides. These are rapid feedback corrections, guided by vision and balance organs. Body posture and the tail refine this control. Banking redirects both wings' forces during a turn. The tail can spread, tilt, and twist, producing drag, some lift, and stabilizing moments. In turbulence, hummingbirds fan it more widely, which may add passive damping at the cost of extra drag. It is an adjustable stabilizer, not the source of hovering. The head can remain remarkably steady at a flower, even while the body shifts beneath it. All of this is expensive. In hovering, the bird must accelerate a column of air downward, simply to remain where it is. It must also overcome wing drag and reverse the wing's inertia at each end of the stroke. An Anna's hummingbird commonly does this at around 40 wing beats per second, while frequency varies substantially among species. Elastic tissues appear to capture some energy as the wings decelerate and return it as they accelerate, reducing the cost of reversal. But the muscles still sustain an exceptional workload. The main downstroke muscle, the pectoralis, and the main upstroke muscle, the supracoracoideus, are both enlarged. Together they account for roughly a quarter of body mass in measured hummingbirds. These muscles are packed with mitochondria and supplied by dense capillary networks, allowing extremely rapid oxygen use. During repeated feeding, hummingbirds can switch quickly from stored fat to newly ingested glucose and fructose, eventually fueling almost all hovering metabolism from recent nectar. That is why nectar is not merely a reward collected by this flight system. It is the high-throughput fuel that makes the system practical, supplemented by arthropods for protein and other nutrients. The energetic margin is still narrow. Hummingbirds feed repeatedly while active, often perch between feeding bouts, and store fat to bridge periods without food. When overnight energy would otherwise run dangerously low, many species can enter torpor. Body temperature and metabolic rate fall sharply, cutting the cost of surviving until feeding can resume. Torpor use varies with species, season, temperature, and body condition, so it is not simply a nightly off switch. It is flexible energy management for an animal whose daytime flight machinery can consume fuel at an extraordinary rate. Other birds may hover briefly by flapping hard, and kestrels or seabirds can remain fixed over the ground by flying into a headwind. But sustained hovering in still air demands the whole hummingbird package. Low body mass, favorable wing area, a stiff extended hand wing, a shoulder capable of powerful long axis rotation, an enlarged upstroke motor, rapid control, and the metabolic capacity to pay for it. Most bird wings are optimized for a forceful downstroke and a partly folded recovery, making prolonged still air hovering both mechanically weaker and energetically prohibitive. So the hummingbird's apparent stillness is produced by continuous reversal. Its shoulder sweeps an extended wing back and forth, then rotates that wing, so both strokes push air downward. The downstroke supplies most of the support. The inverted upstroke supplies a substantial minority, and unsteady vortices help the wings maintain force as their speed and orientation change. By tilting that force and altering the two wings independently, the bird can move forwards, backwards or sideways and correct disturbances almost immediately. Hovering is not one trick drawn as a figure eight. It is a complete mechanical system for creating, aiming and paying for aerodynamic force.